Hello, in this lecture we will discuss about the nested arithmetic. Accuracy due to round of error can also be reduced by rearranging calculations. That means what? Suppose we have to find the value of a function at some point and we want to get accurate result. Due to round of error, we are not able to get proper result. In that case, what we can do, we can rearrange our function in such a way so that the accuracy increase. Okay, so the best example we can see in polynomials. Polynomial should always be expressed in nested form. Before performing an evaluation. That means what? Polynomial should always be expressed in terms of nested form so that we can get much better results. In nested form, the number of arithmetic operation can be reduced. If number of operations can be reduced by somehow then round of error can be reduced by itself. Means what? If we have to evaluate a function, then we will try to write that function in nested form, if possible. Because in nested form, number of operations can be reduced, so round of error will be less. Let us do one example, then this thing can be understood properly. Evaluate function f of x equal to x cube minus 6.1 x square plus 3.2 x plus, I should write separately so that it will be better. Evaluate f of x equal to x cube minus 6.1 x square plus 3.2 x plus 1.5 at x equal to 4.71 using 3-digit arithmetic. Okay. Solution. what we have to do, we have to evaluate this function. That function is what? That is a polynomial. X cube minus 6.1 x square plus 3.2x plus 1.5. We have to compute the value of the function at x equal to 4.71. We have to use 3-digit arithmetic operation. Okay, so what we do, first of all, we'll compute the value of x square, like x is given to you as 4.71. Then the value of x square will be what? It will be 4.71 square. This value is coming out to be 22.184100. Okay, so it will use 3-digit chopping. So x square will be what? 22.1 when using chopping, and x square equal to 22.2 when using rounding. Okay, chopping and rounding, x square value. Now compute the value of x cube. X cube will be what? 22.1 into 4.71. This is the chopped value, and this is what? This is the value of x. This coming out to be 104.091. 1.04.091 chopping. Use chopping. So this is the exact value. Now x cube 104. Use chopping. Okay, and the value of x cube 22.2 into 4.71. It is coming out to be 104.562. So the value of x cube using 104. After this we have to truncate the series. So 104, it will be what? 105, because we are using this. So 105. Okay. Now 6.1 x square. 6.1 x square, that means this term we have to compute. 6.1 x square. It is 6.1 into x square. X square value we computed in the previous by using chopping, 22.1. 22.1. The value is coming out to be 134.81. It is what? So we have to truncate this series. This is 134, and using chopping. Okay, 6.1 x square. 6.1 into 22.2. It is 135.42. Using rounding. Value is coming out to be 135. 6.1 x square. Okay. Now 3.2 x. 3.2 x. 3.2 x. It is 3.2 into 4.71. Value is what? It is 15.072. Okay, it is coming out to be 15.0 chopping. Three 3.2x using, it is 15072. It is 115.1 using rounding. Okay, so the value of the function f 4.71 using chopping is coming out to be, like, first of all we'll compute the value using okay. Let us compute the value of fx, exact value f 4.71. use another pen so that it will be better. F of 4.71. Okay, the value is what? 104.487 111 minus 135.32301 plus 15.072 plus 1.5. The value of 4.7 is coming out to be minus 14.263899. This is the exact value. Okay. Now we'll compute f of 4.71. It is 104 minus 134 plus 15 minus 1.5. It is minus 13.5 using chopping. Sum left to right. We are doing sum left to right. That means after this is what? Using chopping. Chopping. Okay. F of 4.71. It is what? Using rounding. We'll write it later on. First is what? Okay. So let us compute error, relative error. Relative error. Whenever we are finding using chopping. So minus 14.263899 plus 13.5 upon minus 14.263899. What value? It is coming out to be 0.05 chopping. When we are using chopping, then the relative error is coming out to be 0.05. When we are using rounding, relative error it is coming out to be nearly equivalent to 0.06 whenever using rounding. Okay. If we see in chopping or rounding, number of operations. How many operations we have used in chopping in calculating the polynomial value? If we see, first of all, what we have done, we have computed the value of x square, one operation here. In computing x square, two operation. After that we multiplied, there is one operation. Here we have used one operation. There one more operation 6.1 into x square, that is multiplication. After that there is one more operation 3.2 into x. This is one more operation, multiplication operation, or I should write here directly multiplication. One multiplication. Okay. In the previous slide it is also multiplication 6.1, that is one multiplication. There is one multiplication, because x square we have already computed. There is again one multiplication. Okay. So how many multiplication we have used? First we have computed x square, one multiplication, then x cube, one more multiplication, that is two multiplication. Okay, after that 6.1 into x square, one more multiplication, that is third multiplication, and it is what? 3.2 into x, fourth multiplication. So we are having here 4 multiplication. Okay, so number of here 4 multiplication. Okay, addition or subtraction, they are the same thing. This is 1, 1, 1. Okay, this 3 addition. Subtraction, addition, we are taking as addition only. Okay, so 3 addition. So 3 addition. Whenever we are, so they are total 7 operation, 4 multiplication and 3 addition. Now let's apply nested form. Now we'll apply nested form. Nested form of the polynomial. What do you mean by nested form? To rearrange function in such a way so the number of operation can be reduced. So function is given to you what? That is x cube minus 6.1 x square plus 3.2x plus 1.5. Okay, what we do, we'll take x square common from here. We are getting x minus 6.1 into x square plus 3.2 x plus 1.5. Now we will take x common from here. Okay, so x minus 6.1 into x plus 3.2 into x plus 1.5. Okay, this is called nested form of the polynomial. Nested form of the polynomial. Okay, we try to reduce the multiplication of x again by itself. It is x cube. If x is a small number, then x square will be a very small number. Then x cube, it is a very small number. So if we are using finite digit arithmetic, then significant digit can be cancelled. So that's why it's better to write this polynomial in such a way so that the power cannot be shown here. Okay, so now compute the value of f of 4.71. f of 4.71 is what? 4.71 minus 6.1 into 4.71 plus 3.2, 4.71 plus 1.5. Okay, so this value is coming out to be what? Minus 1.39, this and this, minus 1.39 into 4.71 plus 3.2 into 4.71 plus 1.5. Okay, so we are getting here the value we are getting here minus 6.5469 after multiplying this term. 69 plus 3.2 . Okay, so this term is coming out to be okay minus 6.5469. We have to use 3 digits, so just take these two terms into consideration. We are using chopping here. Okay, so chopping, that's why we can cancel this series here. Okay, 4.71 plus 1.5. So what we are getting here, minus 6.54 plus 3.2 into 4.71 plus 1.5. We are getting here minus 3.34 into 4.71 plus 1.5. The value is coming out to be minus 15.7314 plus 1.5. Truncate the series after 3 digits. It is coming out to be minus 15.7 plus 1.5, that is minus 14.2 chopping. This is f of 4.71. Okay, similarly we can f of 4.71, it is minus 14.3 using rounding. Relative error, is coming out to be minus 14.263899 plus 14.2 upon minus 14.263899 0.0045 using chopping. And relative error, minus 14.263899 plus 14.3 minus 14.263899, it is coming out to be 0.0025 rounding. So if you see, error due to rounding is less, it is less than the error in chopping whenever we are using nested form. If we are not using nested form, then the error is what? That is in rounding case 0.06, that is more error, that is more than the nested form, and due to chopping it's 0.05. So here we are having number of operations 7. If we check how many operation in nested form, you can see from here number of operations, 1 subtraction, 1 addition, so there are 3 addition and multiplication, 1 multiplication, 2 multiplication. Okay, so there we are having the total number of operation, in nested form, 3 addition, 2 multiplication, means total 5 arithmetic operation. If we see in simple computation, there are 7 total arithmetic operation. So you can see from here, error in nested form is smaller in comparison to the simple polynomial evaluation, and number of operation is also less in nested form, so round of error can be reduced. So that is our aim. If you go to the first slide, then you will find out if the number of operation can be reduced by somehow, then round of error can be reduced by itself. Or in nested form, the number of arithmetic operation can be reduced. So we have shown here by the example. Okay, next topic is, one more thing. Now we can note one point here. Note, nesting has reduced the error for the chopping approximation to less than 10% of that obtained initially. Initially means what? Simple in function evaluation. For rounding, the improvement has been even more dramatic. If you compare the results, then you can find out the solution. Okay, next topic, condition and stability. Condition and stability. So condition and stability. What do you mean by condition? Let's write, then we'll explain. Condition, what do you mean by condition? It is used to describe the sensitivity of the function. Sensitivity of the function. Stability is used to describe the sensitivity of the process. So conditioning is used to describe the sensitivity of the function. This is the important thing, sensitivity. Okay, if we know the condition number, then we can say something about the sensitivity of the function. Stability is used to describe the sensitivity of the process. Stability. Stability of the so we can say here the sensitivity of the function affects with the change in the argument x is described by the condition number Cn. Condition number Cn. So I told you, like, condition is what? It is used to describe the sensitivity of the function. How much a function is sensitive toward a number. So the sensitivity of the function affects with the change in argument x is described by the condition number Cn. So it is relative change in the function fx for per unit relative change in x. Means what? Condition number can be expressed as the relative change in the function fx for the per unit relative change in x. So condition number is what? That is the relative change in fx. That suppose fx is the original value of the function and fx star is what? That is the approximate value. Okay, let us denote the approximate value by fx star. Then it is equivalent to what? It is relative change in the function fx to the relative change in x. So x minus x star. So condition number is what? That is the relative change, that is the ratio of relative change in fx to the relative change in x. Relative change in x. Okay, so we can write it like that. Relative change in fx to the relative change in x. Okay, so relative change in fx and x is what? That is relative error, we can say. Okay, so I should write it here, fx upon mod of fx upon x minus x star upon mod of x. So relative change in function, or we can say relative error in fx upon relative error in x. So it should be what? Fx minus fx star upon mod of fx. Okay, so let's write. So Cn is equal to fx minus fx star upon fx upon relative change in x, that is x minus x star upon mod of x. We can write it like that, mod of x, fx minus fx star upon f of x into x minus x star. Okay, so Cn is equivalent to mod of x upon mod of fx. Okay, so this term fx minus fx star upon x minus x star, when x star or is approaching to x, that is what? That is the definition of the derivative. Fx minus fx star upon x minus x star. X star is what? That the change in x. That is a very, very small change. So fx minus fx star upon x minus x star, that is equivalent to the, whenever x star is changing to x, then it is equivalent to derivative of the function at x. So we can write it f dash x. So the whole thing, this can be written as f dash x. So condition number, we can write it as x f dash x upon mod of fx. Okay, so this is the definition of the condition number. If condition number is less than equal to 1, then fx is val condition. If Cn is greater than 1, fx is ill condition generally. Okay, so if the condition number is less than equal to 1, then the function is well condition. It is not very sensitive toward the change in x. If Cn is greater than 1, then the function fx is ill condition. That means small change in x can produce large change in fx. So fx is very, very sensitive toward the input of x. Just note down one point. If a small relative change in x produce a large change in fx, that means the output obviously, then the system is said to be a sensitive system as fluctuation in input may break the system. So, if a small relative change in x produce large change in fx, that means if we do a small change, in x, then we are getting a large change in fx, then we say the function fx is very, very sensitive toward the input. If it is not producing large change, then the function is what? It is very, very stable function, we can say. Okay, so that's why ill condition, that means a small change in x produces a large change in fx, then we say the system is ill condition. If a small change doesn't create a large change in the function, then we'll say the function is bad condition. Okay, next is some example. Find the condition number of the function fx fx given as under root x and x cube. Okay, what is the definition of condition number? That is x f dash x upon f of x. If fx equal to under root x, let us take fx equal to under root x, then the derivative of the function is what? 1 by 2 under root x. Then condition number will be what? It will be x, derivative of the function 1 upon 2 under root x upon function under root x. It is coming out to be 1 by 2. So the condition number is what here? 1 by 2, less than 1. Another example, fx equal to x cube, then condition number in this case will be what? Derivative of the function 3x square x 3x square upon x cube is coming out to be 3. So according to the definition we can say fx is ill condition, but it depends on the argument input also. If input is very, very small, then the obviously power of x will be what? X is very small, it is a small number. When we are finding x cube, that is again a small number, and we are using finite digit arithmetic, so it may create problem. So don't think like always we are getting condition number large or it is greater than 1, it is a ill condition. It may be ill condition because here we are having 3, so it depends on the value of input also. In all case it will not be a ill condition, it will depend on the input. Okay, one more example. Fx equal to 1 upon 1 minus 2x plus x square. Okay, compute fx at x equal to 1.01. here function, what we have to do, we have to compute function value at 1.01 solution. So first of all, we'll check whether the function is ill conditioned or well conditioned at the point 1.01. So what we do, we'll compute its condition number. Okay, so if it is asked to find out function value at some point, so it's better to compute the condition number of the function. If the condition number is small, then the function value will be the function at that particular point will give you the better result. But if it is ill conditioned, then you may get error nearest result. Like in this case, fx is what? 1 upon 1 minus x whole square. We can write it this expression like that. And f dash x will be what? It will be minus 2 upon 1 minus x whole cube. It is plus. Okay. And condition number is what? Condition number is x, f dash x upon f of x. Mod x, f dash x is what? That is 2 upon 1 minus x whole cube upon 1 minus x whole square. This is coming out to be 2x upon 1 minus x. 1 minus x. Now compute condition number. We can represent condition number by some number k. Then k at 1.01. What is the value? 2 into 1.01. It is 1 minus 1.01. The value is coming out to be 2.02 upon 0.01. This coming out to be 202. It is large. When the condition number of this function at 1.01 is large, that means the function is very, very sensitive at the point 1.01. So fx at x equal to 1.01 is highly ill condition. Ill condition function. Since x equal to 1 is a singular point of the function, point of the function fx. If you see, at x equal to 1 function is not defined. That's why this one is what? That is a singular point. Point of the function fx. So near this point, near to this point, there are sharp changes in the function, function values. Okay, which make the function highly ill condition. Okay, if you see, the function at x equal to 1.01 is what? Ill conditioned. Why? Because the condition number is coming out to be very large. Okay, at x equal to 1 function is not defined. It is a singular point. So near this point, there are sharp changes in the function value, which make the function highly ill conditioned. I think it is clear. One more example we will take. Find the condition number of the function fx equal to under root x plus 1 minus under root x at x equal to 1, 1, 1, 1, 1. Okay. Solution. Condition number of this function will be what? We will compute condition number of this function. Then f of x is what? Under root x plus 1 minus under root x. Okay, f dash x will be what? It will be 1 upon under root x plus 1, 1 by 2, under root x plus 1 minus 1 by 2, under root x. Okay, condition number will be what? X 1 by 2 under root x plus 1 minus 1 by 2 under root x upon function is what? Under root x plus 1 minus under root x. What is the value coming out to be here? It is coming out to be x under root x minus under root x plus 1 upon 2 under root x plus 1 minus under root x into under root x into under root x plus 1. I think this is the value. We are having here 1 by 2 approximately, because x equal to, we are getting under root x into under root x plus 1 multiplication. Okay, what it is coming out to be 1 by 2. This value is what? X plus under root x plus 1. We take common x plus 1 plus 1 upon under root x. Okay, we can write it approximately equivalent to 1 by 2. This x's get cancelled. So we can not exactly, then the condition number is what? It is coming out to be 1 by 2. Not exactly equivalent to 1 by 2, but nearly equal to 1 by 2. Okay. So in this case, find out function value. Like condition number is what? It is coming out to be less than 1. This condition number is what? It is less than 1. According to it, it should be well condition. Okay. But if we are taking this function, now same function, compute fx equal to under root x plus 1 minus under root x at x equal to 1, 1, 1, 1, 1. Okay, so x at x equal to 1, 1, 1. So what is the function value is coming out to be? f1, 1 function value at x equal to 1, 1, 1, 1 is coming out to be under root plus 1 minus under root. The value is coming out to be under root 1, 1, 1, 1, 2 minus under root this value 105.413 minus 105.409. Okay, how many digits in each number? There are 1, 2, 3, 4, 5, 6 significant digits in each number. What we are getting here when subtracting, it is coming out to 0.004. Here it is only one significant digit. Here we are getting loss of significant digit. We can, so highly erroneous result we may get. Okay, so function value at 1, 1 is coming out to be what? 0.004, and it is containing one significant digit. Even in all previous steps, that number are containing more 6 significant digits. So whenever we are losing significant digits, it is also creating problem or creating error in our solution. So if we modified this function as we have done in the previous chapter, loss of significant, then what we are getting? Fx, we rationalize this function, rationalize this function. Rationalize fx. Okay, what we are getting? We are getting under root x plus 1 plus under root x. Okay, and the function value f at coming out to be under root 11112 plus this value is coming out to be 105.413 plus 105.409. Okay, 6 significant digit. It is coming out to be 1.210.822. It is 0.004743334. We are getting 6 significant digits. 1, 2, 3, 4, 5, 6, 6 significant digits. Here we are getting 1 significant. Even the function is same. This and this both functions are same. But difference is what? Here in one case we are getting 1 significant digit, and in the another function evaluation we are getting 6 significant digits. Why it is happening, that we have already discussed in the previous lecture. This is due to the subtraction between nearly equal numbers. Okay, so here we are subtraction sign is avoided by the addition sign. That's why we are not having loss of significant digit, and in previous case we are having loss of significance. So this is much better result in comparison to the previous. So we will connect this result with the stability of the function. Stability of the function. So that will continue in the next class. In the next class we will discuss about the stability of the process. Okay, we'll connect stability with the loss of significance as well as with the condition number. Thank you.